You can sit now?
Yeah.
Thank you. All right, girls. So we will, so that was Friday's lesson, but we will look at the electromagnetic induction. So in the previous lesson, I think it was the lesson last week on Tuesday, we looked at force on a current carrying wire. So this is, and that is called the motor effect. So in motor effect, what we were given was we were given a current carrying wire, and there was a magnetic field, and when a current carrying wire is placed in a magnetic field, it experiences a force and it moves. And the formula that was used was that induced voltage is equal to BVL. B is magnetic field, V is the, no, sorry, it was BIL. B was the magnetic field, I was the current, and L was the length of the wire and the magnetic field. So what in that lesson, what we were saying was that magnetic field and current together, they produce a motion or a force. And that is called the magnetic force, equals BIL. Now this is opposite to that. So here, there's no source of current in this rod or in this circuit. So this is a rod made up of copper wire or some conducting material. And it is moved in a magnetic field. So rod AB, when it's moved downwards, say for example, in this particular diagram, so when it is moved, the electrons, remember in conducting wire, there are electrons around the nucleus. So those electrons, they experience a force. And when they experience a force, they move in one direction. And why do they experience a force? Because they're cutting the lines of magnetic field. If the wire is stationary, then the lines of magnetic field are not cut. So therefore, electrons will not experience any force. So only when it is moving, and you don't have to move the wire, you can move the magnetic fields. If these two magnets, they're moved upwards and the rod is kept kind of stationary in its place, there will be a relative movement. And whenever there's a relative movement, that means lines of magnetic field are cut by that rod. Therefore, the electrons in the rod, they experience a force and they move. And that force is equal to BVL. B is the magnetic field, V is the speed of the moving rod, V induces the induced voltage, and L is the length of the wire which is inside the magnetic field. Now sine theta comes in. If we look back in this one, if now presently, if you look at the diagram, lines of magnetic field are going from north to south in this direction. This one is moved downwards, which is at 90 degrees angle. So if the motion is at 90 degrees angle, there will be maximum movement of the electrons, or there will be maximum voltage induced. However, if this rod was held in the same direction as the lines of magnetic field are, that means it was parallel, then there will be no voltage induced, because the wire, as it moves, if it was held in this one, it will not be cutting the lines of magnetic field. It will be just like moving in between the lines of magnetic field, not cutting them. So in that case, if it is parallel, induced voltage will be 0. And if it is 90 degrees angle, induced voltage will be maximum. And if it is a complete circuit, then there will be current going through that one. And how much will be induced current? Induced current will be V induced divided by R, where R is the resistance in the circuit. Now, to find the direction of the induced voltage or induced current, we again use right hand. We call it generator rule. So what are, we will be using thumb and the fingers of your right hands. If you could extend your right hand according to the diagram. So now this time, your thumb should be pointing in the direction of the motion. So motion is down the page. So if you point your thumb down the page and your fingers turn your fingers, so they're pointing from north to south. So if you do that, so putting your hand in that position, fingers downward, lines of magnetic field. And if you move your right hand or palm, the palm moves like it comes towards you. If it is coming towards you, that means that the induced voltage, and we're talking about the conventional voltage or the conventional current. So that means that current will be coming, or induced current will be, conventional current will be from B to A. So therefore, this end will be positive and this end will become negative. Let me check my answers if I've used my hand correctly. Yeah. So direction of the induced current is in that direction, which is like anti-clockwise direction. So what it means is, if this one was not connected, now this is connected, so it is making a complete circuit. But if it was not connected, then there will be voltage induced, or this rod will become like a temporary battery. But there will be no current if it is not a complete circuit. So question could be asked is that which end will be positive and which end will be negative. So using right hand rule, conventional current goes from here to there. So that means it will come out from here when the circuit is complete. So this end will be positive and this end will be negative. But remember, electrons move actually in an opposite direction. So electrons will move in that direction, which is A to B. But you will be always asked about the conventional current. So that will be from B to A, making A positive, B negative. Is everyone following so far?
Yeah.
Okay. Now, later on in your own time, you can do some of these questions over here using the right-hand generator rule, and answers are given. So you can try that on your own. Now this was a single kind of wire which was moved in a magnetic field. So as long as there is a movement between the conducting rod and the magnetic field, a voltage is induced. So produce a continuous voltage. What we use is, instead of a single rod, a coil is used. So if you look in this diagram, do you see the new diagram labeled as example of electromagnetic induction in a coil?
Yes.
Okay. So let's see that now in this coil, so this is a wire, just like a solenoid, it has been wound. There's no battery or anything. This is just a meter, okay, a kind of centered meter. And so if there is a magnet here, and magnet has got a magnetic field, okay. So if we look at the lines of magnetic field in this diagram, so lines of magnetic field out of the North Pole, they're coming out of the North Pole and they go into the South Pole. So what happens is, if this magnet is moved towards it, then there are electrons in this coil. So this is made up of conducting material. And because these lines of magnetic field are cutting those electrons only while there's a movement. So only when there's a movement, there will be voltage induced. And if there is a voltage, and what we are saying is that movement and magnetic field together, they produce a voltage or induced current. So there will be movement in the needle. I have kind of posted some videos at the beginning of the lesson, so you can watch those videos, which will show you electromagnetic induction. But I would like to show you a little animation. So if I could go to the animation. Okay. Do you see an animation page, kind of a black screen on my screen?
Yes.
Okay. So first of all, so what we have got is like a coil, as I mentioned in the diagram. Okay, there are only two loops, and that's the magnet. So I will move this one, and you look at the length. If there's a current in the wire, then this lamp will light up. So these are little electrons. So as I move it, So I move it, the lamp lights up, but not while it is stationary. Even though it's inside, there is no current induced. So there has to be relative movements. If I move it back, you can see that lamp flashes again. You can also see these electrons moving. Do you see the electrons moving back and forth?
Yes.
Okay, so that's how a generator works, that what there is a relative movement between a coil and the magnet. So it will be more complicated kind of setup, but nonetheless you can see that when I move it towards it or when I move away from it, and if I just, you can see that now that as long as there's quick movement, there will be a lot of voltage or current induced. Just want to show you quick a generator one. Okay, so generator, you know how in the power stations or like Huntley power station and all that, so what happens is that mechanical energy is changed into electrical energy in a generator. So this one is a kind of example of a generator. So when I drop the water from here, it will move this wheel. So this is like a water wheel. And as a result, this magnet will move. And then you will see the kind of these electrons experiencing a force moving and making the current. So let's see if I turn it on. Okay. So basically that's how the generator works. So this one is an alternating current because as you can see, electrons are moving back and forth. They're not moving in a continuous direction. So you don't need to know into the details of that one. All you need to know is whatever is given in your notes. But this demo, I thought I will show you so you understand a little bit better that how does the generator work.